So last time we were in section 3.3 and we saw that the variance distributes across sums of independent random variables. We also saw the central limit theorem. So let's say that you have a sum of n IID random variables. IID stands for independent identically distributed. So these n random variables are independent and they all have the same distribution. In particular, expectation of x is mu, variance of x is sigma squared. So it's not surprising then that the mean of Sn is n mu, and that the variance of Sn is n sigma squared. But what the central limit theorem tells you is that it's in fact approximately normal for large n, where large n usually means larger than 10. So let's take a look at an example here. Say x is Poisson 1. So you can see what S4 looks like, as well as S10. You can see S10 really does look approximately normal. We also saw another formula for the variance. So the variance is the expectation of x squared minus the mean squared, and tail bounds Markov and Chebyshev. So today we're going to go over the concept test responses from last time, and we'll skip over to section 3.6. Next time we'll do 3.4. So we're calculating variance of a sum of dependent indicators, and also we'll talk about the hypergeometric distribution. So last time, if x is a random variable with expectation of x is 3 and the standard deviation of x is 2, then the probability that x squared is greater than or equal to 40, that's less than or equal to 1/3 is true. Let's see what one student writes. Using Chebyshev on probability that x is greater than or equal to 40, we get k is 1.66, thus it's less than 1 over 1.66 squared, which is greater than 1/3. So I have some issues with this. For one thing, we can't use Chebyshev since x is not necessarily non-negative. So when you take the square root of both sides of this inequality, you cannot conclude that the probability that x squared is greater than or equal to 40 is the same as the probability that x is greater than or equal to the square root of 40. But if you could do that, say that it was true that x was non-negative, then let's see what we get here. So square root of 40 must be 3 plus k times 2. So solving for k, we get 1.66. And so Chebyshev would tell us that probability that x squared is greater than or equal to 40 is less than or equal to 1 over 1.66 squared, which is 0.36. Now, because it's less than or equal to 0.366, means that that for a particular x, it might be less than or equal to 1/3. So you would say maybe in this case. So the correct response was A. So you can compute the variance, square of the SD. You can compute expectation of x squared is the variance plus expectation of x squared, so that's 13. And then you can apply Markov directly to get 13 over 40, which is less than 1/3. So the statement is true. So now we're going to talk about the variance of a sum of dependent indicators, but first in the case of independent indicators. So if you have an indicator, the variance of that indicator is the expectation of I squared minus expectation of I quantity squared. And that is, so the expectation of I squared is 1 squared times p, which is just p, and the expectation of I is p, so we get the variance is p minus p squared, or p times 1 minus p. So for example, let's say that x is binomial, so we know this is a sum of independent and independent indicators, And the probability of each indicator being 1 is p, so the expectation of x is n times p, and the variance is n times the variance of I1, which is np1 minus p. So that proves the formula that we've been assuming. Next, we're going to look at an example where x is a sum of dependent indicators. So here's an example. A building has 10 floors above the basement. If 12 people get into an elevator at the basement and each chooses a floor at random to get out, independently of the others, at how many floors do you expect the elevator to make a stop to let out one or more of these 12 people? So x is the number of elevator stops. So to find the expectation of x, of course, we have 10 indicators, one for each floor, and I2, for example, is 1 if they stop at the second floor, and we can find that probability. Let's call it P1. So that would be 1 minus the probability that it doesn't stop at the second floor, which means that all 12 people don't want to get off at the second floor, and the chance of that would be 9 over 10 to the 12th power. So we get the expectation of x is 10 times p1. Now to find the variance of x, the variance of x is expectation of x squared minus expectation of x quantity squared. So x is the sum of these 10 indicators. So x squared is the square of that sum. And you can write that as a sum of these expectations, expectations of I sub j, as j run from 1 to 10. You can visualize this as a grid. So we have I1 to 10 and I1 to 10 along the vertical and horizontal axes here. And so we get a 100 by 100 grid. And the diagonals are I11, I22, I2, and so on. And so I sub 1, of course, is 1 if they stop at the first floor. I2 is 1 if they stop at the second floor. So I1 times I2 is 1 if they stop at the first and the second floor, and 0 otherwise. So it is an indicator, and we'll call it I sub 1, 2. And the chance that they stop at the first and second floor, we'll call that P1, 2. So I'm just going to rewrite my grid here with these indicators. Notice that we have 10 diagonal indicators and 9 times 10 non-diagonal entries here. So P12 would be easiest to think of that as the the converse. So it's 1 minus the probability that we don't stop at the first floor or we don't stop at the second floor, which we can find using our inclusion-exclusion formula. And so the probability we don't stop at the first floor is the unconditional probability 9/10 to the 12th. 9/10 to the 12th is the unconditional probability we don't stop at the second floor. And the probability that we don't stop at the first and second floor would be 8/10 to the 12th. So that gives us this boxed formula here. So now notice also that P11 would be P1, since P11 is the chance you get off at the first floor and the first floor, which is just that you get off at the first floor. So we can write oh yes, sorry. Right. So we can write these diagonal guys as just I1, I2 up to I10, and so on. And I'll just write this. And so so the 10 diagonal ones, the expectation of x squared, it would be 10 times expectation of I1. And then we have all the off diagonal ones. So we have 9 times 10 expectation of I 1, 2. And then the expectation of x quantity squared was 10p1 squared. So we get the variance is 10p1, which is, oh, I guess, sorry. Let me just write this here. So this is p1, and this is p1, 2. I guess I've been using another color for this. P1, 2, perfect. And then I should be consistent with my coloring here. So this is P1, 2. Great. And then we subtract off 10p1 squared. Okay, so that's the equation for the variance. So now let's recall the multinomial distribution. Say we roll a die 10 times, and so the probability that we have 2 1s and 3 2s, and that goes without saying that then we have 5 non-1 2s. So we have 1 6 squared, 1 6 cubed, and then there's 4 faces that aren't 2 2s or 3s, and we have 5 of those, and then we have our multinomial distribution. So here we do a concept test. A fair die is rolled 14 times. Let x be the number of faces that appear exactly twice. Which of the following expressions appear in the calculation of the variance of x? And so here x is the number face that appear twice. So x is I1 to I6, and I2 is 1 if the second face appears twice, which has the probability given by the binomial formula, and I1, 2 is the probability that the first and second face occur twice, which is given by this multinomial formula. And then, as usual, we have the variance of x is 6p1 plus 30p12 minus 6p1 quantity squared. And so you can see that the answer A is wrong because it should be not 14 times 13, but rather 6 times 5 times that multinomial. Finally, hypergeometric. So this is another example of a sum of trials, of dependent trials. So a deck of cards has G aces. X is the number of aces in N cards drawn without replacement from a deck of capital N cards. So we could have, if it's a regular deck, N is 52, G is 4, N is 5. And we would have then the expectation of X. We have X is the sum of these 5 dependent indicators, where I2 is 1 if the second card is an ace. These are, of course, independent because if the first card's an ace, that affects the chance that the second card's an ace. So we have the expectation of X is N times G over N. And for the variance, we would have we have our indicator I1, 2 is 1 if the first and second are good, are aces. So the variance then, and so P1, 2 is right. So it's it's a multiplication rule. So the chance that the first card's an ace, which is G over N, times the chance that the second card's an ace, given that the first card's an ace, which is G minus 1 over N minus 1. And so we have the variance of X as shown here. And next time we will write this variance formula into another form and then we will start on section 3.4. See you next time.